return to where we were last time with the bubble sort algorithm. And in particular, let's just go through the algorithm one more time, and then we'll do some more analysis with it. Okay, so I'm going to shuffle roughly my cards and deal them out. And what do I have? I got 6, 3, 4, 5, 7, 2. All right. So what's the algorithm? First set is 6 greater than 3, or 6 is in the wrong spot, right? Okay, so switch them. We just did one comparison and one swap. 6 and 4. Comparison, wrong, so swap them. 6 and 5, wrong, swap. So one more of each. 6 and 7, correct. 7 and 2, wrong, swap. Okay, so to be clear, what is the end result of one pass through the bubble sort algorithm? The biggest number card is always going to end up on the far right, okay? Which means with the remaining cards, we can ignore the 7 and concentrate only on the remaining pool, right, of one fewer card. All right, continue again. 3 less than 4, good. 4 less than 5, good. 5 less than 6, good. Wrong, swap. Okay, and then repeat. 3 and 4, good. 4 and 5, good. 5 and 2, wrong. 3 and 4, good. 4 and 2, wrong. 3 and 2, wrong. Swap. Okay, so how many operations did that take? Well, I didn't keep count, but it took some number of swaps and some number of checks. Okay, all right. The actual number that it takes is going to be somewhere in between the best case and the worst case scenario. And let's argue again why the best case scenario would be if they just so happen already to be sorted like they are now. Okay, if that's the case, then I don't have any swaps to do because everything's already in the correct spot. But how many checks do I have to do? Well, I have to do 1, 2, 3, 4, 5 for the first pass. And then what do I know about the 7? It's in the final spot. Then I have to go back and start over. And so then how many checks do I have to do? 1, 2, 3, 4. And then how many the next time? 3, then 2, and then finally 1 at the end. Okay, so let's go back to the iPad for that. How many times did it take? So if we had 6 cards, best case was 5 plus 4 plus 3 plus 2 plus 1 comparisons and 0 swaps. Okay, and 5 plus 4 plus 3 plus 2 plus 1 adds up to 15. Or let's be smart and write this as 5 times 6 over 2 because of our little clever trick from last time. Yes? Okay, what about the worst case scenario? The worst case scenario would be if we had to do a swap every single time we did a comparison. That would occur if the cards just so happened to be in what order? In reverse order, yeah. There we would have 5 plus 4 plus 3 plus 2 plus 1 comparisons and the exact same number of swaps. So a total of 30 ops equals 5 times 6 in this case. Okay, so the way we've basically done this algorithm is the worst case is twice as complicated as the best case. okay? But both of these still depend on n squared, basically, okay? So if we generalize this and we have n cards, best is going to take n times n minus 1 over 2, and worst would take n times n minus 1, double that, okay? Both of those, I'm hoping that you're convinced, are essentially n squared. I'm blowing off coefficients and stuff, but basically they're n squared thingamajigs, right? The complexity grows with the square of the number of cards. Now, we saw this experimentally on Wednesday, right? We'll do some more experiments today to either further justify it or further understand it. But based on the just raw analysis here, like we've cracked it. We know the best case and the worst case for this particular algorithm. We? No. We. Oh, you're getting fancy and saying way instead of we. Wow. All right. So let's go over to yeah. Okay. So I had you guys do the card sorting on Monday, right? So there's 46 of you. You sorted it for 13, 26, and so on cards. We looked at the data and we were pretty convinced that this was an n squared kind of problem, right? Well, the analysis we just did explained why it's always an n squared problem for the particular version of the algorithm that we've implemented, okay, this bubble sort one. Um, Strictly speaking, did we do that with the experiment that I had you guys do with the cards? Does that say anything about the bubble sort method? Why not? Because none of you did bubble sort, right? You didn't even know what the bubble sort algorithm was when I had you sorting the cards. So how did you guys sort them? Well, you just came up with something and did it, right? Okay. So our bubble sort, like y'all sorting, by whatever methods you came up with, the averaging across all 46 of you was that was also an n squared thing. Okay, bubble sort. Uh, I didn't have you guys do it with the bubble sort because it would have had to have explained what bubble sort was before we could have done the sorting. Okay. The other thing is bubble sort with 52 cards really sucks. Okay. So if I don't want to bubble sort with 52 cards by hand, well, fortunately, what do I have in front of me? A computer. Fantastic. So I took my computer here and let's do, well, we just did this with 6 cards, right? Um, and so let me do, so what I've got here is basically I've programmed the algorithm in Python to go through the stacks of cards and look at each card and its neighbor pairwise. And if the one to the left of the one to the right, if they're out of order, then swap them. Okay. And each time I do an operation, I'm going to add 1 to my number of ops. And my number of operations come in 2 flavors. They could be a swap or they could be a check, right? And is there really anything different about a swap versus a check in terms of, like, they're different operations? Yes, but they both require effort. So I'm just going to lump them together and get the total number of operations here. Now, mathematically, we've already figured out that the best case is going to be the number of cards times the number of cards minus 1 all over 2. And the worst case is not divided by 2. Okay. All right. So then I'm going to hand this algorithm a random assortment of numbers from 0 through 5 in our case, instead of 2 through 7. I mean, it's same difference, right? And I'm going to have it sort and keep track of the total number of operations it took to do this for each repetition, keep track of the maximum number that we actually ran into and the minimum number that we actually ran into. And then by keeping track of the total number of ops, I can print however many trials I did, basically the average over those number of trials. Okay, so let's do this for 6 cards, and I'm going to do that 10,000 times. Good? Oops. Okay, so in this instance, what did we get? The first number is the minimum, the last number is the maximum, and the one in the middle is the average over all 10,000 trials. Okay, so what do we see? What's our minimum? 15. Does that jive with the math that we just did a minute ago? Yes. Okay. What about the maximum? 30. Does that jive with the math we did a minute ago? And the average is, well, somewhere in between. Okay, fine. Now, let me change this, and let's say that we do it with 52 cards. What should the maximum and minimum be before I even run it? Or how am I going to calculate that? Well, what was our formula? Yeah, so if I've got 52 cards, the minimum would be 52 times 51 all over 2, or 52 times 26. So somebody calculate that real quick. Like, if only you all had phones in front of you. Okay, so what's 52 times 26? 1352. Okay. And then double that, of course, is 2704, right? And that would be the worst case. All right, so let's run this. And again, I'm running 10,000 trials of sorting 52 cards. It'll take a minute, obviously. And what I want to know is, am I going to actually get, what was it, 1354, 1352, and what was it, 2704? Yeah. Am I actually going to see those two numbers here? What do you guys think? Yes or no? Who bets yes? Who bets no? And like a typical American election, nobody votes. All right, so what do we see? Not those numbers. Okay, why did they not appear, but they did on the previous trial? Okay, yeah, more cards, more variation, but keep going with this line of thinking. Yeah, and that's exactly it. Okay, if I had 6 cards, how many orderings, possible orderings of all 6 cards are there? 6 factorial, right? Because there's 6 choices for the first card, 5 for the second, and so on, right? What is 6 factorial? Times. Yeah. Okay. Which happens to be 720. Okay. Smart ass being all recursive over here. Okay. Yeah. So it's 720, right? Fine. So 720, how many trials did I do? Okay. So the odds of me actually getting one of the 720 arrangements that's perfectly sorted or perfectly opposite sorted are pretty good, right? 10,000, 720, 10,000 is way bigger than 720. Odds are good that I would have hit that. Now, was I guaranteed to? Certainly not. By dumb luck, I could have gotten the exact same order every single time. Not very likely, but it could happen. Compare that, of course, now. How many orderings are there with 52 cards? Well, what's 52 factorial? Oh, I'm going to kill you. Okay. Yes, whatever 52 is times 51 factorial. Yeah, but it's a gigantic number, right? And we're only doing 10,000 of these things. So, do we have a high probability of just happening to get lucky that our randomized arrangement was, in fact, um, perfectly sorted or perfectly anti sorted? Pretty low chance. Okay. So what that means is that the minimum number and the maximum number, the minimum number that we actually got is too high, and the maximum number that we got was too low. Okay, the average is probably about right, um, realistically speaking. Okay, I mean it is an average after all. So yeah, so yeah, the more cards or the more ones that you're sorting, the worse off those two numbers are going to sort of diverge the um, from the mathematical analysis that we did a second ago. Okay, does it make sense why? Right, max theoretical doesn't mean that you actually get it. Maybe you do, maybe you don't. Oui, uno. Okay, so let's kind of look at the data if we did this for a bunch of different trials. Okay, so what I did was I took, I basically repeated the experiment that you guys did on Monday by running my Python program for 5, 10, 15, 20, 25, 30, and so on, all the way up to 50, and that's just where I stopped for sake of demonstration. And I ran through and had it compute for that actual trial what was the minimum number that occurred, the maximum number, the average, and then I also have the theoretical minimum and the theoretical maximum. So I've got where it says min ops here and here. The first one is the theoretical minimum. The second one is the minimum that actually occurred during the 10,000 trials. Okay. And for example, when I did 10 cards, what do we see? The minimum theoretical is 45 operations, and the minimum that I actually ran into was 48. Okay, pretty close, but still not perfectly minimum. Okay, and then the averages are there, and also the same sort of deal on the maximum. Okay, so I can graph all of that and do like we did on Monday or Wednesday, and compute the trend lines for each of these. And the trend lines for the max theoretical and min theoretical are perfect because those were mathematically generated. They weren't subject to experiment. The other three that were subject to experiment uh, all fit with a quadratic. And in fact, look at what all the R squared values are. Okay, that's a little sus. Should it be? Is it probably actually one? No, they're probably like 0.999 something or other, and Google Sheets has just rounded it to make a pretty graph. Okay, but basically, like that's pretty damn good. It's n squared. Okay. All right. So do you guys seem convinced, both from an experimental standpoint and from a purely mathematical standpoint, that this algorithm is an n squared kind of thingamajig? Yeah. Okay. And so if I did, well, for example, let's just be evil. All right, let me do 100 cards. Okay, and I'm going to do two instances of it. All right, so what did I get? Whatever. That took how long, roughly? Maybe a couple of seconds at most. Okay. If I increase the number of cards by a factor of 10, how much longer do you think it's going to take this time? The runtime should increase by a factor of, what do you think? Okay, why 100? Yeah, exactly. Okay. The complexity grows with the square of the number of cards. So if I run this, okay, that roughly speaking was 100 times longer. Okay. Now, is this perfect? No. because they're still subject to the randomness, right? Maybe I just get really, really lucky on one sorting and really unlucky on the other one. But look at the average number of operations here. Okay, now granted, this is just an average, and I only did this over two trials so that it wouldn't take forever, right? How many on average did it take when I increased by a factor of 10 the number of cards? Looks like it's a factor of 100, right? And that's really what this n squared thing means, is that increasing the number of cards by a factor of 10 actually increases the complexity in terms of the sorting by a factor of 100. Okay, that's really, really horrible, because what would happen if I did, well, let's do another factor of 10. All right, start playing the Jeopardy music. I mean, what should we expect to see here? Another factor of 100. Okay, now you might say, why would you ever want to sort 10,000 things? I don't know. I mean, it's not like I've got 10,000 playing cards. Um, but let's say I'm trying to sort, oh, I don't know, records of people for the census. Well, then I'm not just sorting 10,000 things, but probably several hundred million things, right? Because how many people are in the country? Hundreds of millions, right? And if my computer's still not done as fast as it is, right? Jeopardy music continues playing. It will finish. Okay. Um, huh? Yeah. Yeah. I bet you could. Okay. You'd have to be really good. Um, yeah. It'd be like, well, when the chess guy was here last week, did anybody go to that? Huh? Right. Played him blindfolded. Yeah, it's crazy. Yeah. Okay. Well, oh, there it goes. Finally finished. And what do we see? Huh. Looks like about a factor of 100. Makes sense, right? All right. Excellent. So, yeah, it's elucidating, hopefully. So, mathematically, we've demonstrated it. Experimentally, we've demonstrated it. Of course, if the minimum and the maximum are both n squared kind of things, then what is on average going to have to be? Yeah, you can't be better than the minimum, right? You might make the minimum, but you can't beat the minimum by definition. Okay, we uno. Okay, excellent. So, is this the only way to sort cards? Of course not, right? There are other methods of sorting that are maybe a little bit more efficient. So let's look at another algorithm, and we'll talk about this one more on Monday also. So this algorithm is called merge sort, and worst case, it still does terrible. Okay, if the cards are reverse sorted, right, you've gotten really, really unlucky. So the way merge sort works is basically says, so they've got an example here for um, eight cards. Let me actually sort of divide that into four piles of two. Okay. So what's actually happening is this is a recursive algorithm. We're going to divide the pile and sort of partially sort the pile, and then kind of go back up the chain and partially sort the results and sort of merge these two quasi sorted things together. And here will be the last stage to get the final sorting of the whole thing. Okay, so the animation a little bit harder to follow what's going on here compared to bubble sort. Okay, but this is an example of a recursive way of doing things, and B, what we might call a divide and conquer kind of approach, right? if I can divide the problem into two problems that are half as big, yeah, I still have to solve those two problems, and yeah, I have to combine the results, but maybe I can do a little bit better than the bubble sort algorithm. And on average, it does. Okay, it's average and um, uh, and in fact, worst case performance is not in squared, but rather in log n. Okay, now logarithms. We all love them, don't we? No, you don't like logarithms? Oh, that's unfortunate. When did you guys first learn logarithms, by the way? Pre-calc? Okay, why did you need them suddenly? Yeah, deal with exponents, right? Uh, what if I told you that that is completely ahistorical, the way that we teach logarithms? Would not surprise you? Okay. Uh, Logarithms actually have their birth in trigonometry, not with dealing with exponentials. Uh, yeah, if we've got a little bit of time at the end, I'll tell you that tale real quickly. Okay, so the log of n. Typically in computer science, not always, but typically when we say log, like, okay, so let me actually back up. In math class, if you saw log of n, what would you assume? It's base 10, and if you wanted to compute the log of a specific number, which button on the calculator would you hit? The log base 10 button. Okay. Um, what other bases are there? Well, there's the natural base, which we call base E, and we abbreviate it how? LN for short. Okay. Although in most math classes, or okay, um, basically in any math class, if you're talking about a logarithm, you're talking about a natural logarithm. Like in calculus, it's almost always a natural log. Okay, so it's the case that in some books, lots of books, when you see log in a math book, you should assume it's actually base E. Okay, now nowadays I think most people use ln instead, but like in advanced books, when you see log, it just means natural log. In computer science books, what do you think the base is? Base 2. Well, that makes sense, right? Okay, now, strictly speaking, does it matter which base you use? No, because if I give you a logarithm and one, like, let's say I ask you to compute the log base 7 of 5, how would you do that? Well, yes, you plug it into a calculator, but where's the log base 7 button on your calculator? There isn't one, right? So how do I compute the log base 7 if I don't have a log base 7 button? We just give up and fail? Kids these days. Some calculators might actually have such a feature, but they don't need to because, Mr. Litz, do you remember? Yeah, the change of base law, right? And in fact, I can change it from any base to any other base. Oh, I'm sorry. That, right? The change of base law. Okay, so it actually doesn't really matter which base logarithm we use, but in computing, because stuff is all binary anyway, often we're going to work with log base 2. Sometimes you'll see LG for log base 2 in books. It depends on the source, but the maybe the moral of the story though is whenever you're looking at a new source, be it Wikipedia or a textbook or an article or something, the first thing you got to figure out is okay, well, which base logarithm do they mean? Um, so in most math classes, it's going to be log base E. In theoretical computer science, which is basically what we're doing, it'll be log base 2. And in science or any kind of practical mathematics, then what is it usually? log base 10, right? Okay, which explains why on your calculators, what log buttons do you see? Base 10 and base E, okay? Yeah, and by the time you make it to computer science, you've outgrown a calculator, and so, yeah, no need. Okay, so, right, so let's go back to the merge sort algorithm. This one, at worst case, is n log n. Now, what's the relationship between n and log n? Which one's bigger for large values of n? You had a 50-50 chance, but I'm afraid you chose poorly. All right, let's graph the two things. Huh? At least you chose. Yes, at least you did. Okay, let's go to Wolfram Alpha and back to the iPad. All right, so uh, let's graph x. Okay, so um, there on the graph. Uh, oh, it's done. It's done as a parametric plot. That's not what I want. Um, we'll just do the log by itself. Okay, so here's the plot of it from -6 to 6, and this is the natural log, although, like I said, it doesn't really make a huge deal. Which base that we use? Okay, what would the graph of x look like? Straight line, slope 1. Okay, so it would go through this point where my finger is, because notice that the axes, the scale of the axes isn't a square axis. So for large values of n, who's bigger, x or log x? X is way bigger, right? Log x is smaller. So uh, log x is smaller than x, right? And so log n is smaller than n for large n. And so if I multiply both sides by n, what do I have? That, right? Now, how do I know that I didn't have to like flip the inequality or do any sort of nonsense like that? Right? I just multiplied both sides of this inequality by n. Do I have to flip the inequality? Why not? Yeah, because I didn't multiply by negative, right? Now, it is possible for log n to be negative, by the way, but that would require n to be between 0 and 1. And fortunately, that's off the table because what kind of n are we talking about? Large n, right? The business of algorithm analysis is asking what's going on for big values of n. Forget small values of n. Who cares? It's the long-term behavior that we are worried about. Okay, and since n is always a positive number here, no negatives, no need to flip the inequality, and so this is strictly less than n squared. So if I were to program the merge sort algorithm, okay, and go through and do all those Python, have it run 10,000 trials and so on, first off, would we expect that on average it's going to be faster than the bubble sort method? I would hope so. Okay. And if we then looked at and did the plot of the complexity and I did a curve fit, then it would fit more towards this than it would to n squared. Okay. And for large values of n, of course, so actually this bears speaking or bears pointing out, let's say that with the bubble sort algorithm, if I multiplied the number of cards by 10, what did we see the effect was on the runtime? Factor of 100. Okay, so if I increase the number of cards by 10 for the merge sort, I would go from some number to not quite 100. It would be whatever 10 times the log of 10 is. Okay, well, what is the log of 10? Roughly. Okay, so instead of increasing by a factor of 100, I would increase by a factor of, what was it, like 23 point something, right? That's pretty good, right? We've cut the work by a factor of 5 compared to our other algorithm. Okay, however, what's sort of the downside or a downside to this merge sort algorithm is the algorithm is a lot more complicated to write down, right? And furthermore, it's recursive. But we all love recursion by now, right? Yeah. Okay. All right. So it would be more complicated to program, as you can see, right? They've got a whole bunch of different instances of it, and great. All right. So it's a better algorithm. The best algorithm that I know of is called quicksort, and this one, ironically, has worst case performance worse than the merge sort, but average performance is usually roughly the same. Okay, so it's kind of an interesting thing that a supposedly good algorithm, like it's on average faster than merge sort, even though they have the same complexity. But worst case, it's actually worse, which is just sort of interesting. Okay, but what I think I maybe, if I didn't mention it Wednesday, I certainly meant to. Algorithm analysis, which is what we've been doing all of this week and we'll finish on Monday, right? We've spent 4 days on this topic. You could spend an entire semester on this kind of topic. And those of you who want to be CS majors, guess what? Yes, CS 243, okay, is entirely about all of this stuff. Okay, so what we've done is basically the tiniest amuse-bouche of um, of what algorithm analysis is. Okay, so if you think this is dreadful, well, that's a valid opinion. Okay, just beware of CS 243. If you think this is awesome, well, get ready for CS 243. Right? Okay. Um, oops, that's not what I meant to do. Let's see. The last thing I wanted to do is let's go back to the iPad and um, let's talk about what happens if I repeat, like what happens if I have a procedure that I know its complexity and I start to repeat it some number of times. Okay, so suppose that proc for process is big O of f of n. Okay, in our example for bubble sort, the process was the bubble sort process, and the f of n was what for bubble sort? It was n squared. Okay, so bubble sort was O of n squared. Merge sort, we'll take Wikipedia's word for it right now that it's O of n log n. Um, and other algorithms have, whatever other complexities. Okay, so let's suppose that I take my bubble sort algorithm. Okay, I know its complexity. And let's suppose I do the following. Let me just say n. That I do n instances of the bubble sort. Okay, so what this would mean is I have 10 cards, I do the bubble sort thing 10 times. I have 100 cards, I do the bubble sort thing 100 times, 1,000, 1,000, and so on. Okay, let's call this our new process. what I want to ask is, what is the complexity of this new process if I do the bubble sort algorithm n times? Okay, now first off, what's the complexity of a single instance of the bubble sort algorithm? Just doing it once. N squared, right? We've seen that decidedly. Okay, what do you think happens if I do it n times to the complexity? So 10 times is sorting 10 cards, 100 for 100, and so on. What do you think that does to the complexity of a single bubble sort? I'd like to convince you that it multiplies it by n. You guys don't seem convinced. Okay, it multiplies it by a factor of n. So what would it be in total then? Order big O of n cubed. Okay. Now, let's maybe think about why that's the case. Okay. Um, if I let's take the example of going from 10 to 100, right? If I go from 10 cards to 100 cards and I'm only sorting it once, how many times, or what's the sort of worst case operation length to go from a factor or not 10 cards to 100 cards? I've the complexity goes up by how? A factor of, okay, I've got 10 cards. I sort them. I now have 100 cards. I sort them. We should go up by a factor of 100. Why? Because what is bubble sort? It's O of n squared. We saw the complexity grew with the square of the number of cards, right? So 10 times as more cards, 100 times as hard of a problem, okay? If I'm doing that problem 100 times, well, then that's 100 times harder than doing it just once, right? Okay, so that's why it's going to multiply like this, right? So the moral of the story here is if you have a process and you know its complexity, it's whatever, and you stick that thing inside of a for loop that depends on the number n, then you've just multiplied by n for the total complexity of the thing with the for loop. Okay, so this would be a cheesy example, but let's say that I have 10 cards and I want to sort them 10 times. Okay, that would take 10 times as much work as just sorting once. Yeah. Now, let's say that I repeat this again. Let's say that I have 10 computers and I'm going to have them each do 10 cards 10 times. Okay, what would be the smart way of having the 10 computers do this? Huh? Oh, okay. It's interesting. Let me rephrase. I want each computer to definitely do it 10 times, right? So I'm going to do the whole thing 100 times collectively. I'm sort of distributing the runs across 10 computers. What would be the really stupid way to do that? Well, okay, you could do it 100 on one computer, or you could do 10 on the first computer, and when that's finished, you do 10 more on the second computer, and when that's finished, you move on to the third computer, right? Would you guys agree that that would be silly? What would be much more efficient? Do all of them at the same time. Okay, let's suppose that I'm being really stupid, okay, and I'm going to do them 10 on the first computer, and I won't start the second computer until the first computer's finished, okay? And I do each one 10 cards 10 times, okay? So that takes some amount of complexity, right? All right, let me change the problem and say, okay, fine. Now I want to do 100 computers, each to sort 100 instances of 100 cards. Okay, how much more complex is that than the original case. I argue that it's a factor of 10 to the fourth. Okay, why 10 to the fourth? Well, what's the complexity of doing a single sort and multiplying the number of cards by 10? There's not 10 times harder, 100 times harder. So there's 100, okay, or 2 factors of 10. All right, if I do that 10 times, there's another factor. And if I've got 100 computers, there's the other factor of 10, right? So 10 to the fourth. You guys don't seem convinced. Pretty convinced? I don't know. Mr. Inshill, are you going to buy it? $3.99? You think I could get $19.95 out of you for it? No? I got a $19 Fortnite card. Does anybody want it? No? You guys don't even get that joke anymore? No? Okay. All right. So where are we going to go with this to finish things up on Monday, right? So if we stick, or for now, if we know the complexity of a particular procedure and we stick it inside a for loop, that depends on n. That's a key assumption there. Then the complexity grows by just multiplying, okay? And if I stick it inside nested loops, then, well, it just keeps multiplying. But what's true about the procedures that we've sort of looked at thus far? Okay, bubble sort, the linear search, which was, I think, the way that you did your sorting. Like you looked through your stack until you found the 2, and then you put it right. Okay, so that's a procedure, right? The Towers of Hanoi, we looked at that. But at least for the complexity question, we've only answered how to do this for certain algorithms. And in particular, the ones that we've looked at have not been recursive, right? But could we ask the same question if I have a recursive algorithm? How can I get a sense of its complexity? We could ask that question, right? All right, now let's take the Towers of Hanoi, since that's where we actually started with the whole discussion of recursion. How many steps did it take to solve the Towers of Hanoi? Well, it depended on the number of disks. Okay, we saw that. And what was the complexity of it if there were 5 disks? How many operations did it take? No, it was worse than that. It's 2 to the 5 minus 1. Okay, so 31 total operations, right? And so what did we find for the Towers of Hanoi? We found experimentally that Towers of Hanoi is O of 2 to the n minus 1, which is the same as 2 to the n. Okay, it grew exponentially with the number of disks. Okay, but how could we demonstrate that other than, like for the Towers of Hanoi problem, it was pretty obvious when we thought about the solution why it was exactly that. Okay, what about this merge sort algorithm? Well, let's figure out its complexity. We know the answer because Wikipedia said it, but let's see why it is that. Okay, so how we mix this stuff with recursion will be the thing we do on Monday using what's called the master theorem. Okay, all right. So if you have not already gotten and or taken your exam, you know where to find them, right? If you need some scratch paper, that's fine. You should not need anything else. If you guys would do me a favor and make sure you put your name on it, and underneath that write 11 o'clock, since that's which class you're in, and make sorting these easier, so I don't have to do the bubble sort with your exams. All right, and I will see you all on Monday.